Hello. Hello, everyone. I'm Han from eBay. I'm a software architect in eBay and also an open source OVN developer. So today, my topic is large-scale overlay networks with OVN. So I'm going to share with you some experience we run overlay networks in eBay with OVN and the problems we found and the improvements we did. So the agenda is basically I'll go through some background here for OVN, and then I'll go through each of the control plane components one by one in OVN, and then I'll talk about scaling ACL and scaling nested workloads like Kubernetes running on OVN. Running on VMs, which is running on OVN, and how to scale them. So first of all, some background of OVN. Could you raise your hand if you ever used OVN? Well, quite a few. So basically, OVN is an SDN solution developed by Open vSwitch community, which is well known for its virtual switch running OpenFlow. And for the same community has best expertise for Open vSwitch, developed this SDN solution for operating OVS and running overlay networks and all the SDN features. It supports OpenStack and Kubernetes with its own plugins, which is networking OVN for Neutron and OVM Kubernetes for Kubernetes. And it has a lot of features for SDN, including full L2, L3 virtualization, and Layer 2, Layer 3 gateway, and a lot of features like stateful firewall and distributed load balancer. So almost everything you can think of as an SDN solution. And here's the distributed control plane. Basically, this is some unique design of SDN, of OVN compared to some of the first generation of SDN solutions. So it's not, there's no single point of bottleneck like centralized. I should not say this, but I mean, it intends to distribute the node instead of everything computed in centralized. So it has a centralized part and also a distributed part. And central part contains basically two databases. One of the databases is northbound database, which contains the abstraction of the logic objects such as logic switches, logic routers, and ports, and ACL, load balancing, such kind of things. And then there's a southbound database, which stores basically the objects that can be understood by the distributed part. The most important thing is the logic flows. That is similar as the OpenFlow rules, but it doesn't contain any physical information. Instead, it's just very high-level logical information. But the format is very similar as the OpenFlow rules, so you can have match conditions and actions. There's a NNASTYA daemon, which is running on the central node, responsible for translate these logic objects in the northbound DB into the objects in southbound DB. In southbound DB, apart from the logic flows, there's also port binding information, which is the physical mapping between the mapping between the logic ports and its physical location, so that overlay network can work. And the distributed part is the OVN controller, which is running on all the hypervisors. So the OVN controller is responsible for translating the logic flows into physical flows that is running on OVS, which is responsible for taking care of the packet forwarding finally. And the whole architecture is based on OVSDB. So OVSDB is very important here. And everything, the solid line in this picture is OVSDB protocol. So basically, the NNASTYA daemon will get a notification from the northbound DB and then translate into southbound, right into southbound DB. And the OVN controller will, in turn, get notification from southbound DB and translate into OVS flows. So it's a very solid pipeline and elegant architecture. But since overlay network is very complex, so there's a lot of features to be implemented, but it also means this is a little bit hard to scale, especially in the control plane. So I'll talk about the challenges we encountered. Firstly, the first challenge we encountered is actually not the central part as we expected, but it's in the distributed part in the OVN controller. Since the OVN controller needs to compute a lot of information, basically it's a big size of data. And scale environment, there's a lot of logical ports to be processed on each of the hypervisor. If you consider any-to-any connection in a VPC or in Kubernetes environment, right? So potentially, every work node in the hypervisor could talk to a lot of other work nodes in the same network or logical networks connected by logic switches and logic routers. So each hypervisor needs to understand how to reach to the other remote logic ports. So that means a lot of information to be processed. And also, there's a lot of changes in the cloud environment. So like VMs up and down frequently. So it means there's a lot of notifications to be processed by each of these OVN controller. And more important part is that the OVN controller, when it's trying to compute the OpenFlow rules, there's a lot of inputs to be considered. This is a very complex situation. If you look at this picture, it's pretty much the dependency graph of the OVN controller. So there's a lot of inputs, almost 17 or 18 of them. And there's southbound DB tables and OVS tables locally, and also intermediate results computed during this processing. So to implement something efficient, this is poses some challenge. So the first approach, original approach taken by the community is simply recompute everything when any input changes. And the benefit is that it's relatively easy to implement and maintain, but the problem is it's slow and the CPU is occupied in all the hypervisors like 100%, and the control plane latency is very high. That means when you boot a VM, it takes a long time to be really accessible. So our solution here is implementing an incremental processing engine. So we implement that with this DAG diagram to represent the dependency. And each node has its own data and the dependency links to the inputs. And it has a full compute handler to write how to compute the output according to the input. And then there's also a change handler that can process the data, the changes only and efficiently to calculate just the data information. So this engine runs in a DFS post-order, traversing the diagram, and then if any input changes, it tries to firstly invoke the change handler if it exists. And if it doesn't exist, or if the change handler cannot handle this change, it will fall back to the full recomputing. So the beauty of this mechanism is that you don't have to implement everything incrementally because that's super complex. And you can just implement the ones that matters much so that most frequent changes can be handled incrementally and fast. So with this consideration, we implement change handlers for many of the inputs, which are the orange boxed inputs, including port binding change, logic flow change, etc. So anything related to a VM or pod container up and down are handled incrementally. So with this change, we did scalability testing in an environment with 1K simulated hypervisors with 20 bare metals and create and binding 10K ports on these 1K hypervisors. And the compare with the version that didn't do it, so it's very impressive improvement. And especially in the CPU utilization, it's almost 90% reduced. And also latency improvement is also very significant. So we did a test on top of those 10K ports and create and bind one more ports end to end. So basically start from the creating in the northbound DB until the port is processed by NNASTYA, and finally the flow is programmed on all the hypervisors so that the traffic end to end will go through. So this latency has also dramatically decreased. And then we did some larger scale testing with 20K ports, 30K ports. So we can see there's still some growth with this CPU cost and also the latency. The first reason is the next bottleneck actually is not in the flow computation, but in the OVS flow installation. And then we have some improvement idea work in progress, because that's just a no-hang foot. We already have the incremental processing. To incrementally install the flow is very easy. And next point is port binding handling, which is happening on the local hypervisor, which cannot be, the incremental processing handler is not yet implemented. So if the port is banded on the local hypervisor, the OVN controller on this hypervisor will still recompute everything. So that takes a lot of time. But all the other hypervisors will incrementally process that change. So CPU utilization on other hypervisors will not be very high, but the end-to-end latency still will be high. And also, latency is also due to the NNASTYA, OVN NNASTYA recomputing. I'll introduce later. So this is the next steps for the incremental processing. First 2 points, I just mentioned some low-hanging fruits. And then this whole idea is incrementally processing the changes. But we discussed with, so the patches have been reviewed and a lot of discussion and also a lot of help from the community. But we end up with some conclusion that we may need to find something more powerful to do this job, because if you look at the input processing, it's very, very much like flow processing, data flow processing. So there's the some open source framework brought up by a researcher in VMware, and it's called differential data log, in short DD log. It can incrementally processing the data flows. So we're trying to utilize this in the long run. And I introduce this in more detail later for talking about NNASTYA scaling. But there's some people actually asking me for the patches because they want this feature immediately, because the data flow DD log implementation will definitely take some time. So for someone who needs this, here's some link and rebased on the branches. And there's some other improvements potentially can be done and work in progress. I would just skip it because of time reason. Okay, so the next bottleneck is the southbound DB. For the southbound DB, it's obvious because it's centralized database. And if there's a lot of clients connecting to this central DB, for example, 1,000 hypervisors or 2,000, even more, it's easy to become a bottleneck. So it's related to the number of clients, and also it's related to the size of data. And also the rate of changes will also impact this scalability. The first problem of DB scalability is the OVSDB probe mechanism. It is a mechanism that is built in OVSDB between the client and server so that they can detect if the link is down or not. If the link is down, the client or server will, so the client will initiate reconnection. This causes a scale problem because the default probe is 5 seconds. And OVSDB response can occasionally be longer than 5 seconds because OVSDB is a single thread process. And there's some features like DB log compression takes a lot of CPU. And even if there's a huge, very big transaction coming to the OVSDB, it will also take a long time because you need to both processing the transaction and push to all the clients. So in this case, client will reconnect, and client reconnecting will pose even more nodes to the server. So it will cause more client disconnect, and then more clients even causing more node. This will be a cascade failure. When client reconnect to the server, you will need to resync all the data from the server for whatever is interesting. So this is the reason why client reconnect poses a node to the server. And this problem is actually solved. I will introduce it in next slide. But the solution to the southbound DB probe problem will be just simply increase the probe interval. But just to be careful that you need to tune this parameter in both client side and server side, because it's easy to ignore in this server side. And next problem I introduced is related to just what I mentioned about the client resync all the data from server side. OVSDB works in a way that the client has all the clients, each of the clients has the cache, and it works on the cache. So clients monitor the server for whatever it's interested in, and then in the beginning, when the client connects to the server, all the data will be downloaded to the client side, and then it's a long connection monitoring the server. Any change happens, it will be notified. So this mechanism is not a problem, of course. But the problem is when server restart or failed over, or whatever reason the connection is reset, then the client will have to, all the client will have to resync the data. That causes a lot of node in the server. And if you see the right bottom picture, the CPU is almost 100% busy, and the memory also spikes similarly. And the upper picture is showing that how long it takes for the server to come down in this case. If it's 1K hypervisor and 10K ports, it takes more than 30 minutes. And more ports takes even longer. It's like 30K ports takes almost 2 hours. So the improvement we did is very straightforward. So we track and maintain the recent history transactions in memory and disk on each of the server node. And client side can request from a specific point with a specific transaction ID that just give me only changes after this point. Because when the server starts, clients are all alive and all the caches are still there. So this reduces most of the data transfer and processing. So improvement is very obvious. And third problem of OVSDB is that, sorry, I forgot to mention that the fast resync mechanism actually is merged in master and will be released in OVS 2.12. But it only works for cluster mode because other modes don't have that unique transaction ID capability. So I'll talk more about the cluster mode then. Because of this, we're prioritizing the using of cluster mode. This feature actually has been supported there for a long time since version 2.9 as the experimental support. But we're not using it. We're using the active standby approach with pacemaker. It works, but it's not very good as active. So because of that fast resync feature, we even further optimize this clustering support. So basically, the feature is very good, and the code quality is high. It works in small scale very good, but when we test in the big scale environment, we found a lot of basically 4 major issues. So first one is like high CPU node, and then if you update from 4-node node, it takes a very long latency. And then there will be needle flapping problems during the scale testing. And also, the client will be reconnected when failover happens, even if the client should not be impacted. Those problems are all actually, so 3 of them merged in master, solved. All problems has been solved, and one of them still work in progress, but with a workaround. So it's very easy to I'll briefly talk about this. So the need flapping problem, actually, there's a quick workaround just to increase the injection timeout for the raft. But we're still working on the final solution about configurable injection timeout. So I'll talk about the test result of the scalability test result of cluster mode. Basically, we had the same 1K hypervisors testing environment with 3-node cluster, and we tune this injection timeout. Basically, it's hard-coded. Just as I mentioned, this is the only workaround to 10 seconds, and then we keep creating and binding ports up to 10K. And during this testing, we randomly kill and restart servers. It's basically stress testing. And in the end, this testing went through very well, and all the port creation bindings are successful. And so actually, that fast resync helped a lot in this case, because otherwise it would pose a lot of node in the server and testing cannot be finished. So one of the interesting things I want to discuss is a future improvement. It's in the to-do list. It's not in the progress, but I think it's important because what if we want to support more hypervisors to a larger scale, like even 5K and 10K? We can add more nodes in the cluster, but a raft cluster doesn't scale out, right? Because if you add more nodes, their write operation will take longer because to reach a consensus. Basically, it's a consensus protocol for HA, not for the scalability. And another thing is to add multiple threading supporting OVSDB. Of course, this is the right thing to do. It will help, but there's a lot of reasons it's not easy, and it won't solve the end problem, because even if you have multi-threading, you have still a limited number of cores in the server, so in the end, it won't scale out. So a much simpler approach I think we can take is if we have the precondition that to make sure there's no write to the southbound DB from the hypervisor. So if all the updates to the southbound DB can only be done from north side, from the either NNASTYA or CMS side, basically the chassis, encryption, encapsulation, and the port binding, those updates can be done actually from northbound and CMS. And if we don't use those advanced features like dynamic ARP learning, then there's no need to write the southbound DB from hypervisor. And if that's true, we can do a very simple approach, is just to add n number of read-only replicas to the south side of the southbound DB. So this is very easy to scale out. And you can imagine you have 10 such kind of nodes. Each node support just 1,000 nodes, then you have 10K nodes supported. It's very, I think it's a very good way to scale out in the future. And next one, bottleneck is the NNASTYA, the daemon in the north, but it's not a Nike. It's not single point of failure. But the problem is the size of data is big, and then you have a high rate of change. You have a similar problem with the OVN controller, basically. And current implementation is the NNASTYA is always recompute everything. So this is very clearly discussed in the community, and it's work from the community. eBay is not yet involved in this work, but I think it's a very important thing to mention here for the complete list. So OVN NNASTYA increment processing is going to use differential data log, DD-log. So DD-log is basically you define the inputs and outputs as relations, just like relational DB tables. And then you define the declarative rules, how to convert the inputs to the output. So it's very straightforward approach for something like NNASTYA, because it also has the same structure like input, output, and rules to convert into output. Output is the open, the logic flows basically. So the effort actually can be reduced by OVN controller, I think. And I won't talk to more details here. But I'll recap for the scaling bottlenecks of each of the control plane components, basically NNASTYA, southbound DB, and OVN controller. And we have some more interesting scenarios I want to share with you. First thing is security group or network policy, basically, which use the ACLs in OVN. And next one is about nested workloads. So the ACLs in OVN is the way to actually support a lot of features such as OpenStack security group and Kubernetes network policy, which is something like a stateful firewall, right? But so the typical use case is all the member of the same group can talk to each other. Of course, you can have similar variations, like application A talks to application B, but it's all, the important thing behind it is similar. So the basic, I call it naked approach, is to write for the same as for OpenStack or Kubernetes plugins, to write the rules like this. So it has to represent, for each hypervisor, it has to represent like one rule for one output port, but in each rule, you have to explicitly write out all the IP addresses. This is a big O n squared problem. And then address set is introduced in OVN. That alleviates that problem. It becomes a big O n from the CMS perspective. But the number of flows in OVS actually is still big O m multiplies n. So m is the number of ports on a hypervisor, n is the number of ports in the group. And our solution here is the port group, which is already released in 2.10. So with this port group feature, the CMS, Kubernetes plugin, and Neutron plugin only need to write one rule to represent just the scenario we just mentioned. So you have the port group name, and then it generates the OVN NNASTYA will generate the address set automatically for you. And the task for CMS is only to create this port group with the ports, and addresses of ports already defined in the port itself. So there's two related links. One of them actually written by Daniel from Red Hat. Thank you. And another advantage actually by this approach is not only simplifies CMS implementation, it also reduces the number of flows in the open vSwitch finally, because if you have multiple ports on the same hypervisor belong to the same security group, then the conjunction behavior or action from OpenFlow in OVS will take effect. So convert this from m multiplies n problem to m plus n problem. It's much more efficient than before. And there's some more improvement I think we can still do in the to-do list. So although port groups improve this pretty much, but in the worst cases, the number of OpenFlow rules still huge in the hypervisor. And what we can do to further improve this is, I think, to carry the security group ID or application ID, whatever ID, in the tunnel header. So that ID can be carried by the packet. So you don't have to list everything in OpenFlow rules. So in the OpenFlow rule, you just maybe need one flow here to say whatever ID is in this header, I will allow it or deny it. So there's some limitations, of course. So, it basically works for ingress direction only, but I think it's still pretty much a valuable feature to do. And the next one is about scaling the nested workloads. Major use case is running Kubernetes in the VMs, which is running on OVN. So we don't do tunnel over tunnel in eBay because we think it's not very efficient. And we just run containers as bridge mode in the VMs. So container doesn't know anything about the OVN overlay running behind the VM. You only see the VM. And in the VM, we set up bridges running only bridge mode, not overlay or no tunneling there. And the problem is, how do we scale this? So first approach we take, actually the current approach we took is using app proxy in the VM. So VM is running in this hypervisor, and the hypervisor will be running OVS, which is connected to managed by OVN. And since OVN doesn't support microlearning, so we did a trick, which is the app proxy, so that anything, when the logic router asks for the MAC address using app for the port IP, the app proxy on the VM will discover it and reply with VM's MAC address. So this information will be populated actually to the through the MAC banding feature, or you can say IP MAC banding feature of OVN. So this information will be learned by the OVN by the OVS flows and pop this information to OVN controller, and OVN controller will further populate to the southbound DB. And the southbound DB MAC binding table will be learned by all the hypervisors. So all the hypervisor Open vSwitch will get this information. It works, but it will require basically VM and ports being in the same subnet. And also, it might be not very reliable because it relies on dynamic ARP message populated to southbound DB. So think about if southbound DB is occasionally or transient failure in some period, those ARP messages will be lost forever unless you have some automatically or periodically sending GRP, those kind of mechanism. Otherwise, it will be a problem. And scalability is basically big O N. N is number of ports. Because each port will be mapping to one entry in the MAC table, MAC banding table. And the approach we want to take next, actually we had a POC, it works pretty well, is that adding static routes in the logic routers, so that the logic router has just static routing entries added by the cloud management system. That is a more declarative approach. You don't need to rely on any dynamic ARP. You don't worry about any message loss, so because it's declarative. The desired state will be there. And it also decouples the subnet between the VM and ports. So for example, in this VM, there are 4 ports, all of them on same subnet. It might be a very small subnet, /25, to save IP addresses. But you only need this one entry in the routing table saying, for this subnet, just the next hop is the VM. This entry in the logic router. So it will be, packet will be delivered to the VM. And within the VM, you can use many different mechanisms to forward the packet to the ports, maybe just a simple bridge or some more advanced mechanism, or IPv9, for example. So the best part of this mechanism is that it's much more scalable. So assume you have many ports on same VM, and you assign just a subnet to that VM. Then you have only one entry for all those ports. You don't have to have one-to-one mapping between the port and MAC binding table like the previous approach. And in the worst case, if you still want that extreme flexibility or IP mobility, that you don't want strict ports in your VM belongs to just one subnet, then you can still use the NNASTYA, but you lose the scalability, but you can still keep the flexibility. Okay, so this is most of my talk. There's some references. There's actually the first, there's the ongoing work about splitting OVN from the OVS, but I think otherwise all the other links should be still okay. And I would like to thank for the community. Actually, it's an awesome community for the OVN development. So most of the content I talk is about the improvement we did in eBay, but there's a lot of other work, other very good improvements did by all the different people in the community. And it's awesome. I think with all this effort, OVN should be getting even better. So thank you. So we still have 2 minutes. If you have any questions, please come to the speaker. Okay, if no questions, thanks again.